afternoon. My name is Merly de la Cruz and I am the last reporter of the chapter 5. We have the 5.8, which is the real gases, and the 5.9, the characteristic of several real gases, and we have the 5.10, the chemistry in the atmosphere. Thank you.
First, we had the 5.8, the real gases.
So what is a real gases? A real gases are non-ideal gases whose molecules occupy space and have interactions. Consequently, they do not adhere to the ideal gas law. So a real gases is a gas that does not behave as an ideal gas due to interactions between gas molecules. A real gas is also known as a non-ideal gas because the behavior of a real gas is only approximated by the ideal gas law. So, an ideal gas is a hypothetical concept. No gas exactly follows the ideal gas law. We must correct for non-ideal gas behavior when pressure of the gas is high and the temperature is low. Under these conditions, concentrations of gas particles is high and attractive forces become important. So we have here the two graphs. First, we have here a plot of PV over nRT versus P for several gas at 200K. So the ideal gas law is written in an empirical form. PV over nRT, where P is pressure, V is volume, T is temperature, N is the amount of substance, and R is the ideal gas constant. So it is the same for all gases. And we have here the graph. In the graph, we have here the PV over nRT. We have the 0, 1.0, 2.0, and the lower part we have P, ATM, 0, 200, 400, 600, 800, 1000. And as you can see, the ideal gas side, pantay sila ng 1.0. So, the ideal gas, we have here the H2, which means a molecular hydrogen gas. The CH4, the methane in the center, and then in the inside of the graph we have here the N2, which is the molecular nitrogen, and the CO2, molecules of carbon dioxide. So the second graph, we have here a nitrogen gas at 3 temperatures. So in the PV over nRT side, we have the 0.6, 1.0, 1.4, 1.8. And the lower part, PTM, we have here the 0, 200, 400, 600, and 800. The ideal gas is aligned also, is pantay also sila ng 1.0. And we have here the 673K, 293K, and 203K. So that is the graphs. So we have here the van der Waals equations. Van der Waals equations is an equation of state that corrects for two properties of real gases: the excluded volume of gas particles and attractive forces between gas molecules. So we have here the equations of van der Waals. The corrected pressure times the corrected volume equals nRT. So the corrected pressure, or P ideal, we have the P OBS plus A open parenthesis N over V close parenthesis squared times the V open parenthesis the V minus in B. So that is the corrected volume, or V ideal, equals the nRT. So that is the equation of van der Waals. So let's proceed to the 5.9, which is the characteristic of several real gases. So we have here the characteristic of real gases. For a real gas, the actual observed pressure is lower than the pressure expected for an ideal gas due to the intermolecular attractions that occur in real gases. So a real gas is a gas that does not behave as an ideal gas due to interaction between gas molecules. So next we have here the value of a reflex, how much of a correction must be made to adjust the observed pressure up to the expected ideal pressure. A low value of a reflects weak intermolecular forces among the gas molecules. So we have here table 5.3 the values of the van der Waals constants for some common gases. So we have here the name of the gases, the He, the helium, neon, argon, krypton, xenon, oxygen, nitrogen, chlorine, carbon dioxide, ammonia, and the last one we have the water. So the HA we have here the symbol HE in the A, ATM minus L squared over MOL squared. So letter A, and then we have here the 0.0341, Ne 0.211, 1.35, 2.32, 4.19, 0.244, 1.39, 1.36, 6.49, 3.59, 2.25, 4.17, 5.46. And the B we have here the L over MOL 0.0237, 0.0171, 0.0322, 0.0398, 0.0511, 0.0266, 0.0391. We have the 0.0318, 0.0562, 0.0427, 0.0428, 0.0371, 0.0305. So that is the table 5.3, which is the value of the van der Waals constants for some common gases. So that is the value of the value of the helium, neon, argon, krypton, carbon dioxide, nitrogen, hydrogen, and many more. So next we have the 5.10, the chemistry in the atmosphere. So we have here the air pollution. Air pollution is a mixture of solid particles and gases in the air. Two main sources is the transportation and production of electricity. So it can be car emissions, chemicals from factories, dust, pollen, and mold spores may be suspended as particles. Combustions of petroleum produces CO, which is the carbon monoxide, CO2, the carbon dioxide, NO, and NO2. We have here the NO2 along with unborn molecules from petroleum. Next, we have the nitrogen oxides due to cars and trucks. So we have at high temperatures, N2 and O2 react to form NO, which oxidizes to NO2. The NO2 breaks up into nitric oxide and free oxygen atoms. Oxygen atoms combine with O2 to form ozone or O3. So we have here the NO2 J into NO J plus OJ. We have the OJ plus the O2 J and into 03 O3 rather J. So that is the nitrogen oxide. So we have here the concentration for some smog components versus time of day. So we have the graph, the other side, the concentration. We have the 0, 0 0.1, 0 0.2, 0 0.3, 0 0.4, and 0 0.5. We have here a time of day, 4 o'clock, 4 a.m., 6 a.m., 8 a.m., 10 a.m., noon, 2 p.m., 4 p.m., and 6 p.m. So we have here the molecules of unborn fuel. We have a 8 a.m. The concentration, we have the 0.5. Hindi pa siya nakaabot ng 0.5. So in the other pollutant, we have here the 2 p.m. The 2 p.m. No. It's not a 2 p.m. Noon. 12 noon. At exactly 0.3 concentrations. So we have here the 0.3 O3. In the noon also, 12 noon, we have a 0.2 concentration. And the NO2, we have a 8 a.m. and hindi pa siya naaabot ng 2. And the last one, we have the NO. Hindi siya 6, mga 7, 6.30. Nasa 6.30 siya na time. Tas nasa 1 and a half siya ng concentration. So this is a graph of a concentration for some small components versus time of day. So next we have the sulfur oxide due to burning coal for electricity. So we have the sulfur produces SO2 when burned, and SO2 oxidizes into SO3, which combines with water droplets in the air to form sulfuric acid. So we have here the formula, I think, is open parenthesis IN cool close parenthesis plus O2 open parenthesis G and close parenthesis into SO2 J 2SO. In the middle we have 2SO 2 G plus 0.2 rather G into 2SO 3J G. We have the SO3 G plus H2O open parenthesis I close parenthesis into H2SO 4 open parenthesis, AQ, and close parenthesis. So I think this what do you call this one, formula here is a what do you call this one, is a procedure in how to form a sulfuric acid, I think. So sulfuric acid is very corrosive and produces acid rain, and use of scrubber removes SO2 from the exhaust gas when burning coal. So we have here the last one, we have a schematic diagram of a scrubber. So a scrubber works by spraying a wet slurry of limestone into a large chamber where the calcium in the limestone reacts with the SO2 in the flue gas. And also what do you call this one? Scrubbers are one of the primary devices that control gaseous emissions, especially acid gases. So scrubber can also be used for heat recovery from hot gases by flue gas condensation. So that is what happened in the picture, from the small container from the large container into the small container. It goes transferred to the small container. So that's all I understand about the schematic diagram of a scrubber. And that's all. Thank you.